Hey there, everybody. We're going to look at time dilation a little bit more. Kind of worth the time to get used to the different things about which one's the relativistic time and the proper time and all that stuff, and a couple other ways of justifying the ultimate speed limit and even actually justifying why time dilation happens at all is the goal today. So we're going to start out. I'm just going to review over this trip question here about Alpha Centauri is 4.3 light years away, and that's from the Earth's person's point of view. And so we could calculate how long it should get there at a certain speed, and if we calculated how long the trip would seem to the people on the trip, right? So remember we're going to be seeing something to do with length soon, because they recognize like, wait, it only took 1.4 years to get there. Everything would seem like normal motion to them while they're traveling, but the trip wouldn't take as long for some reason, so they'd have to kind of see something to do with that, right? So what they'll see, spoiler alert, is they'll see that length contracted. The length that they see that they need to go, they will see as smaller. Think of the muons that hit the atmosphere. They're created in the atmosphere and fly towards, travel down towards the Earth. They manage to get to the Earth before they decay, because they see that distance, and so they would see that distance as smaller, right, in order to justify how that's possible. Now, this example here, though, we can introduce or look at a concrete example, like with numbers, to do with the twin paradox. So the spacecraft is traveling for the 1.4 years and so on, but then it turns around and comes back another 1.4 years to return to the Earth, right? So how long did the trip take from the Earth observer's point of view? Well, of course, it would just be the 4.625 or 4.5262 or whatever, times 2, right, there and back. And then has the space traveler, aged more or less than the Earthbound coworkers? Well, they would have only aged the 1.4 times 2. They'd only aged 2.8 years, right? And so, although this is, of course, strange and unfamiliar, it is absolutely what would happen. We have technologies, satellites, and GPS navigation, and so on. Those GPS in particular have super accurate clocks in them, and the time that the signal takes to get from your phone to the satellite, and from your phone to another satellite, and so on, is all used to calculate your location. And those calculations, have to include the effects of special relativity and the fact that time is slower because of the satellite's motion. So we knew this in advance, and the calculations were done, and the satellites were designed and made according to those calculations, and everything worked. There's also, by the way, effects on time due to not being as close to the Earth's gravity, and that's actually even a bigger effect. But again, all those calculations were done because we knew about them. I like to think of the possibility of us having discovered special relativity, time dilation, and so on, if we didn't know about it, and we had this great idea to do GPS navigation. All of the calculations would have been wrong, right? The locations wouldn't have worked, and we would have been wondering why, and maybe that could have been a way that we would have discovered that time slows down when things are moving fast, and changes to do with position relative to masses due to gravity as well. It's not how our scientific history played out, but I wonder if there are other civilizations out there, if they discovered it that way, or think of the possibility that we could have, right? And it's just kind of neat to think about. Anyways, this apparent twin paradox. Okay, so this is all good, right? The twin paradox comes in where we talk about how, since motion is relative, the Earthbound observer could consider themselves to be moving relative to the spacecraft. Like, instead, the spacecraft stayed still, and somehow the Earth blasted off and went away and came back, and so on, right? And so this would be, of course, a paradox, since they can't both be both older and younger than each other. Like, it's one has to actually be younger than the other, right? Or i.e., the space travelers could consider themselves as stationary, and the Earth went away from them and came back. But and so in that scenario, I'm going to reveal that later. But the motion is relative, right? So we'd say, okay, they would see. This is true, by the way. Like, when the the spaceship is flying off towards the galaxy or star or whatever it was. If they had binoculars or a telescope or whatever, and they looked at the Earth, people on Earth as they're going away, the people on Earth would appear in slow motion to them. And then, the picture of the Earth observers observing the people in the spaceship, they would appear slow motion. This is what would happen. So, when they return to Earth, they might incorrectly expect the Earthbound people to be younger than them. So the but is in this, is that uniform motion is relative. Okay, so this, how can this apparent contradiction be explained, thus saving, special relativity from an unexplainable, illogical paradox that means it's not true? Well, special relativity is about, is the fact that uniform motion is relative. So the claim of uniform motion relative to the spacecraft is not valid. Like Earth can't be consider itself as uniform motion because an acceleration had to happen, right? Clearly, the Earth didn't accelerate away from the spacecraft and then turn around and come back. Like that's just not what happened. And so the spacecraft is the one that did the moving relative to Earth, and that's what matters, right? So the spacecraft had the rockets needed to accelerate away and then to turn around. Earth did not. So Earth did not accelerate. Earth did not move in the scenario. Okay. The spaceship was the actual traveler, and so they're the ones that actually age less, right? So there isn't a paradox, and it just seems like there would be if you don't understand that the acceleration of the two objects relative to one another is the distinguishing feature, really. So just another time dilation question here for practice. So they're an astronaut, and I like this example because it's very obvious which time's which here, I think. So they're playing a song, right? And it's a 4-minute song. So you're on a spaceship playing a song. You're not at in motion relative to that, CD player, MP3 player, phone, or whatever you're playing it on, right? So that would be the proper time, of course, right? Because they're not moving relative to the device. Anyway, so proper time, 4 minutes. Okay, so then you're looking for the relativistic time. What an Earth observer, it says, indicate the time measured by both the astronaut in the fast-moving spaceship and the time measured by mission control at home, listening to a radio broadcaster or whatever, listening to it happen in the spaceship, right? So calculations, here's the equation that we know from time dilation. We developed it ourselves, like it's not magic, right? Put the numbers in, so the proper time and the speeds and so on, the c squareds cancel out, and we get that the song would last an extra 2 minutes, right? Because we'd hear it sort of a little bit in slow motion. It would last extra 2 seconds, right? So, or 0.02, I don't know, I have to do the calculation there, 0.02 of a minute, I have to say, I suppose. Whereas if the spaceship was going 0.9, 90% the speed of light, that would stretch out to 9.18 minutes, right? So that that 0.02 of a minute of 60 seconds would be 1.2 seconds. So this would be 4 minutes and 1.2 seconds, whereas the 0.18 of 60 seconds is 10.8 seconds. So 9 minutes and 10.8 seconds, depending on whether that meant. Yeah, you know what I mean? Like this, if this is counting like a clock, that could mean 2 seconds, but it depends on what that was meaning. Anyways, so paraphrasing here, of course, mission control would hear the song playing in slow motion. The astronaut inside the rocket would measure the time to be 4 minutes, because otherwise they'd know they're really moving, so quote unquote, and that physics experiment can indicate that, right? The aging process, the person would age less too. So using same numbers here, 4 in terms of years instead of minutes, they can do the same calculation, would spit out the same answer, right? If they're going the 9.9c, they would age 9.18 years. They would say, oh man, the trip was almost 10 years. And people on Earth would say, oh, no, it was just, it was just 4 or whatever. Yeah, it was just 4 years. So notice this isn't like an eternal life or endless youth or anything, but it does allow the fast-moving father to return. It just slows time down, right? But it would allow the father to return to Earth someday physically younger than the son. So you'd have to think of how that would work. Like if the son was 2 years old, and then the trip happens, and it's a 10-year trip, but that experience is 20 years for the child. The child's going to be 22, and the father was, think of the numbers there. The father's aging slower than the son, right? So you have to just think of how the numbers would work there. Notice that, of course, the father can't end up younger than the son was when they last saw each other, right? It's not time travel. It's people describe it as traveling into other people's future, right? So you come back and you've only aged 4 years, but 10 years has gone by on Earth, right? So you traveled into other people's future. You've only experienced 4 years of life. It's a kind of like time travel, but it's just time travel into other people's future. So that's done there, and then this is just a little bit more about the speed limit business, right? So nothing can go faster than the speed of light. It's the ultimate speed limit, and so on. So we saw justifications of this already with the laser or light beam chasing a ship, and also the relativistic version of E equals mc squared, where you had the best mass and the increase due to in energy due to the speed. That was the one that was like the Pythagorean theorem, right? It was understandable-ish, but I mean not required for the course. So this conclusion also can come mathematically from the time dilation. So also you can say also comes mathematically from the time dilation equation that we developed, right? And if you look at the equation, you can kind of see why, right? So if the speed was c, then that would be c squared of c squared would be a 1. So we'd have root of 1 take away 1, which would mean root of 0, which would be 0. That would mean mathematically, that would mean if your something managed to go light speed, that the time dilation equation would lead, which is true about the object, would lead to a divide by 0, and you can't divide by 0, and so you can't go light speed. I was never super satisfied with that as a reason. I like these other ideas that we've seen about the light beam chasing the ship and so on. But math has the power to do that. If it can't happen mathematically and the math represents reality, then it can't happen in reality. There's a lot of ifs there, though. Like if the math represents reality, then it can't happen, right? So what about faster than the speed of light? That would give a negative number. Well, can you do roots of negatives? No, right? So it can't happen mathematically. And since the math represents real life, if it does, right, then that mathematically, that means it can't happen. So, yeah. So time dilation is real. Video coming at you here. And then.
So why don't we ever see this in everyday life? Well, at the slow speeds we move here on Earth, motion's impact on time is so tiny, we don't experience it. But the effect is real and can be measured. To do this, all you need are a couple of atomic clocks and a jet airplane. And this experiment was carried out in 1971 when scientists flew an atomic clock around the world and then compared it to one on the ground. As Einstein predicted, the two clocks no longer agreed. They differed by only a few hundred billionths of a second, but very real proof of motion's effect on the passage of time.
Einstein's theory has been tested again and again and again, and it all hangs together. It really forms the basis for the way we understand much of the way nature works.
These effects, which used to be considered sort of obscure and very small, are very in your face with today's technology.
With the discovery of this unexpected link between space and time, Einstein realized that the two could no longer be thought of as separate things. Instead, space and time are fused together in what came to be called space-time.
Einstein unified the idea of space with the idea of time into this four-dimensional structure called space-time.
And this fusion of space and time would lead Einstein to perhaps the most mind-bending realization of all: the sharp difference we see between past, present, and future may only be an illusion. In our day-to-day lives, we experience time as a continuous flow, but it can also be useful to think of time as a series of snapshots or moments. And everything that happens can be thought of as the unfolding of moment after moment after moment. And if we picture all moments or snapshots lined up, every moment here on Earth, every moment of Earth orbiting the sun, and every moment throughout the entire universe, we would see every event that has ever happened or will ever happen. Every location in space and each and every moment in time. From the birth of our universe at the Big Bang, some 14 billion years ago, to the formation of stars in the Milky Way galaxy, to the creation of Earth 4.5 billion years ago, to the time of the dinosaurs, to events happening on Earth today, like me working in my office. Thinking about space-time like this led Einstein to overturn our everyday picture of past, present, and future. To get a feel for this, you have to think about the seemingly simple concept of now. For me, a list of things that I consider to be happening right now might include the tick of noon on my office clock, my cat just now jumping from the windowsill, things happening far away, like a pigeon in Venice taking flight at this very moment, a meteor just now hitting the moon, the explosion of a star at the far reaches of the universe. These and all other events that I think are happening at the same moment in time, but in different regions of our universe, make up what I intuitively think of as now. You can picture them as lying on a single slice of space-time. Let's call it a now slice. Common sense would say that you and I and everyone else will agree on what's happening or what exists right now, moment after moment after moment. That is, we would all agree on what lies on a given now slice. But Einstein showed that, strangely, when you take motion into account, this common sense picture of time goes out the window. To see what I mean, think of space-time as a loaf of bread. Einstein realized that just as there are different ways to cut a loaf of bread into individual slices, there are different ways to cut space-time into individual now slices. That is, because motion affects the passage of time, someone who's moving will have a different conception of what's happening right now. And so they'll cut the loaf into different now slices. Their slices will be at a different angle.
That person who's moving will tilt the knife, will be carving out these slices at a different angle. They won't be parallel to my slices of time.
To get a feel for the bizarre effect this can have, imagine an alien here in a galaxy 10 billion light years from Earth. And way over there on Earth, the guy at the gas station. Now, if the two are sitting still, not moving in relation to one another, their clocks tick off time at the same rate, and so they share the same now slices, which cut straight across the loaf. But watch what happens if the alien hops on his bike and rides directly away from Earth. Since motion slows the passage of time, their clocks will no longer tick off time at the same rate. And if their clocks no longer agree, their now slices will no longer agree either. The alien's now slice cuts through the loaf differently it's angled toward the past. Since the alien is biking at a leisurely pace, his slice is angled to the past by only a minuscule amount. But across such a vast distance, that tiny angle results in a huge difference in time. So, what the alien would find on his angled now slice, what he considers is happening right now on Earth, no longer includes our friend at the gas station or even 40 years earlier when our friend was a baby. Amazingly, the alien's now slice has swept back through 200 years of Earth history and now includes events that we consider part of the distant past, like Beethoven finishing the Fifth Symphony.
Even at a relatively slow speed, we can have actually tremendous disagreements on our labeling of now, what happens at the same time, if we're spread out far enough in space.
And if that's not strange enough, the direction you move makes a difference too. Watch what happens when the alien turns around and bikes toward Earth. The alien's new now slice is angled toward the future. And so it includes events that won't happen on Earth for 200 years. Perhaps our friend's great-great-great-granddaughter teleporting from Paris to New York. Once we know that your now can be what I consider the past, or your now can be what I consider the future, and your now is every bit as valid as my now, then we learn that the past must be real. The future must be real. They could be your now. That means past, present, future, all equally real. They all exist.
If you believe the laws of physics, there's just as much reality to the future and the past as there is to the present moment.
The past is not gone, and the future isn't non-existent. Past, the future, and the present are all existing in exactly the same way.
Just as we think of all of space as being out there, we should think of all of time as being out there too. Everything that has ever happened or will happen, it all exists. From Leonardo da Vinci laying the final brushstroke on the Mona Lisa, to the signing of the Declaration of Independence, to your first day at school, to events that from our perspective are yet to happen, like the first humans landing on Mars. With this bold insight, Einstein shattered one of the most basic concepts of how we experience time. The distinction between past, present, and future, he once said, is only an illusion, however persistent. But if every moment in time already exists, then how do we explain the very real feeling that time, like this river, seems to endlessly rush forward? Well, maybe we've been deceived and time does not flow. Perhaps the river of time is more like a frozen river, with every moment forever locked in place.
The most vivid example about the way the world is has to do with this flow of time. Physics does radical violence to this everyday experience of time.
Our entire experience of time is constantly in the present, and all we ever grasp is that instant moment.
There is nothing in the laws of physics that picks out one now over any other now. It's just from our subjective viewpoints that it feels like things are changing.
Just the way an entire movie exists on a reel of celluloid, think of all moments of time as already existing too. The difference is that in the movies, a projector lights up or selects each frame as it goes by. But there's nothing in the laws of physics that selects one moment over another. Our brains may create this impression, but in reality, the flow of time really may be nothing more than an illusion.
So, as you can see, there's more to it than just the time dilation equation. The loaf of space-time and the angle of the knife thing. There's other calculations later on if you go on further in this. Don't need to worry about it for now, but I just want you to get a feel for, the situation. So I'm going to keep going here.
But if time, like this frozen river, does not flow, and all of time is out there, is it possible to travel to the future or the past?
Now departing for 50 years in the future, like 24.
And if we could time travel, would it be anything like what we imagine?
To catapult you through time into a world that is yet to be. The Time Travelers.
Suppose something goes wrong with the time machine again.
Roll a switch, Jack.
Can we go anywhere we want at any time?
We're going to attempt time travel.
No one outside of Hollywood has made a working time machine just yet. But surprisingly, time travel might be possible.
Now boarding flight 24 to black hole Cygnus X1.
One way to travel through time is to make use of a strange feature of gravity. The familiar force that keeps our feet planted to the ground can have a profound impact on time.
See you later, sir.
Right. Much later. So, how can gravity be used to make a time machine? Well, Einstein's theories show that gravity, like motion, can affect time. It's as if gravity can pull on time, slowing its passage. And the stronger the gravitational pull, the more time slows. Here on Earth, the effect is too small to notice, but still very real. Compared to someone living on the top floor of a skyscraper, someone living on the bottom experiences time elapsing a little slower because gravity is just a tiny bit stronger closer to the ground. But if you could travel to a black hole, the effect of gravity on time would be huge. Formed when large stars collapse in on themselves, black holes have immense gravitational pull, millions and even billions of times stronger than the Earth's. And if someone watched you travel close to a black hole, they'd see time for you slow down dramatically.
You near that black hole will appear to your friend far away. You moving slowly, talking slowly, biologically, aging slowly. To them, years are passing, while for you it might be minutes.
So, depending on the black hole size and how close I get, if I spend an hour or two in orbit, something like 50 years will have passed back on Earth. I will have traveled to Earth's future.
Hello, sir.
Hi.
Long time no see. Time travel becomes you.
Thank you. Kind of like a fountain of youth.
Time travel would be using gravity, but they could have done this simpler and just to be to a special relativity where he could have gone on a really fast journey, right? So zip out for a year and back for a year at a really fast rate. The year being the time spent in the ship. You come back, 2 years later, and maybe it's 100 years later on Earth or something, right? That's the same kind of effect. Traveling into others' future is what I was talking about before. But yeah, later on, just to, I thought I'd include as well the general relativity idea, so you have a good idea overall of things, even though we're not doing any of the calculations to do with general relativity. So
when I return, I'll find myself in the future. Everyone else will have aged 50 years, but me, a couple of hours. Now, time travel to the future is one thing, But what about time travel to the past? Well, that might be possible too, using something predicted by Einstein's equations known as a wormhole. If wormholes exist, they would be kind of like shortcuts through space-time, tunnels that would link not just one place with another, but also one moment with another.
A wormhole would connect one part in the space-time to another part in space-time, which is in an earlier time, like a sort of subway system through time.
So let's say I wanted to go back in time and meet myself at the beginning of this program. If a wormhole connected here and there, all I need to do is step through. Hey, good to see you again. Thanks. Good to be back. Well, that would be kind of weird, but the real problem with time travel to the past is that things would get pretty confusing pretty quickly. I mean, imagine I were to change something about my past, like preventing my parents from meeting. Would that mean I'd never be born?
If you do travel to the past, you can't change things that we know are true about the past because they already happened.
So if you go back and kill who you thought was your grandfather, that must have been some other guy you thought was your grandfather, and everything must somehow become beautifully self-consistent, even if it's in a twisted way.
And if you can travel to the past, why haven't we been overrun by tourists from the future? I mean, think about it. We haven't seen any intrepid time travelers popping into and out of our world. At least most people don't think we have. So it's probably safe to assume that time travel to the past just isn't possible. At least not yet. But since the math hasn't yet ruled it out, we can't dismiss time travel to the past entirely.
They're not mentioning here, it's just the idea of the physically trying to go through a wormhole if they exist. The gravity gradient would just tear things to shreds. They call it spaghettification. Your head and your feet would experience vastly different gravity forces and so on. So there's physical limitations involved, likely making it not possible, even if wormholes do actually exist. A lot of sort of like speculation going on in this section for sure, but that's fun.
The math hasn't yet ruled it out. We can't dismiss.
So it's not at all clear that it could ever be a practical reality. But at least in principle, it doesn't seem to be forbidden.
My guess is that it's impossible, but it's striking that we still haven't been able to rigorously prove that.
While it seems likely that traveling to the past is out of reach, what about the fact, so common to our everyday experience, that time itself seems to move in only one direction? We call this the arrow of time.
The arrow of time is probably the most blatant fact about the universe we live in that we don't completely understand. Why we live in a universe that has a directionality to time is a mystery.
This is not true of space. In space, I can go from New York to Chicago, and then I can change my mind and go from Chicago to New York. So there is a one-way aspect to time that we don't understand at a fundamental level.
Why doesn't it go backwards? What does it even mean that time goes forward from the past into the future?
So what can we say about where the arrow of time comes from? Why do we only see events unfold in one direction? Why don't we ever see them happen in reverse order? Well, it must be the laws of physics. I mean, surely they don't allow something like this to happen. Well, actually, they do. The laws of physics are the mathematical equations we use to describe everything from the behavior of atoms to the swirl of galaxies. They've been devised and confirmed through centuries of observation and experiment. But surprisingly, there's nothing in the laws of physics that says events have to unfold through the familiar sequence we call forward in time. According to these equations, events could just as well unfold in reverse order.
Most of the equations we use to describe what we see in the universe around us don't have an arrow of time attached to them. They're equations that work equally well, moving forward in time, moving backwards in time.
There's this contradiction between the physics, which seems fundamentally reversible, and so much of our life that seems irreversible.
Though it flies in the face of everyday experience, the laws of physics actually say bizarre things like these are possible. But how could this be? Well, the answer is not as far-fetched as you might think. Here's why. We all know what will happen if I drop this glass of wine. Now, the idea that this mess could somehow reverse itself and form back into a solid glass filled with wine seems absurd. But according to the laws of physics, this can happen. All I need to do is reverse the velocities of everything. Every piece of glass, every drop of wine, every molecule and atom in the liquid, glass, table, and air. Just reverse all their velocities. And voila! So, if the laws of physics don't care about whether glass is shatter or unshatter, why don't we ever see them unshatter? How can we square the laws of physics with our everyday experience? Something must be missing in our understanding, but what? What's responsible for the arrow of time? Like many good mysteries, this one leads us to a graveyard in our search for clues. In Vienna, near the final resting places of Beethoven, Brahms, Schubert, and Strauss, is 19th century Austrian physicist Ludwig Boltzmann's tombstone. Etched on top is an elegant equation, S equals K log W. It's the mathematical formulation of a powerful concept known as entropy. Entropy is a measure of something that we're all familiar with, disorder or randomness. And it's an important idea because there's a tendency of everything in the universe to move from order to disorder. Here's a way to get a feel for the idea. Take my book, all 569 pages of it. It's very ordered, with the first page followed by the second, followed by the third, and so on. But now, let's tear the pages out and let entropy go to work. As you can see, the pages become very disordered. And the reason is simple. There is only one way for them to land in order, but a huge number of ways for them to land out of order. And so it's much more likely that they'll land in a total mess. And this is what we experience in our daily lives. Things move from order to disorder. In this case, from a neat ordered book to pages that are randomly scattered. Everywhere we look, we see examples of entropy or disorder increasing with the passage of time. An egg breaks and splatters. Ice cubes lose their orderly shape as they melt into water. Billowing smoke becomes increasingly disordered.
Ordered states become disordered states. And that appears to be perhaps the direction of an arrow of time.
We see sort of degrees of messiness, a measure of disorder, tend to increase in one direction of time.
And so that, for Boltzmann, begins to create an arc of time.
So maybe this is the answer. Maybe the arrow of time comes from the tendency of nature to evolve toward ever greater disorder. This sure seems like progress, but there's just one small problem with this reasoning. Because the laws of physics don't distinguish between the future and the past, entropy should increase not only toward the future, but also toward the past. And that makes no sense.
That's like saying that entropy should increase in either direction that we look. We could look backwards in time and it should increase. We could look forwards in time and it should increase.
That would mean the pages of my book in the past would be disordered and then come together to form the neat ordered book in my hands. And when's the last time you saw something like that happen? How could our everyday experience be so at odds with the laws of physics? There must be a piece of the puzzle that's missing. If we're sure the past had to be more ordered, and that everything tends toward disorder as the equations of entropy tell us, is there something else besides the laws of physics that might explain this? Well, think of hitting a baseball. The laws of physics can help you predict where it will land. But those laws are not the only things you need. Run the film backwards, and you can see that you also need the initial conditions, like how hard the ball was hit. Similarly, if the laws of physics can't give us an explanation for the arrow of time, maybe we need to look further to the initial conditions of the universe. That brings our attention back to the Big Bang. If the history of the universe were like a movie and you ran it backwards, you'd see an increase in order the further back in time you go. Gradually, today's universe, with billions of galaxies clumped here and there, would turn back into clouds of gas and dust as everything contracts.
So these clouds of gas and dust move closer and closer to each other, so that if you get far enough into the past, they're squeezed into a smaller and smaller volume.
We've now come to the place where the buck finally stops. If this represents all of space at each moment of time, then we can see there simply isn't any more space and time before this single moment. So the ultimate source of order, of low entropy, must be the very beginning of the universe, the Big Bang.
The Big Bang is a highly ordered state. It's probably the most ordered event in all of physics. And so everything that has come after that has been an increase in disorder.
What the Big Bang gives us is a reason why the universe might look different when we look backwards in time versus forward. Moreover, when we go back to early times, the universe should have looked not just different from today, but highly ordered.
Why was the entropy low? We don't know. But at least we know that there was a point that the universe began in when the entropy was low.
So our best understanding is that the Big Bang is what set the arrow of time on its path. You can picture this as something like a wind-up clock. Just as the stored energy of a tightly wound clock is released as it unwinds, the universe has been unwinding since the Big Bang, becoming ever more disordered.
Our universe started out in a very unusually orderly state. And that's ultimately responsible for the fact that time seems to have a direction.
We don't yet know why our universe began in a highly ordered state, but the fact that it did means that every time a glass shatters, it's actually carrying forward something set in motion billions of years ago. The glass breaks, but doesn't unbreak because it's following the natural drive from order to disorder that began with the Big Bang.
We only ever move from the past to the future. And everything we see around us, all the changes from the formation of stars to our lives, is all little epiphenomena, surfers riding the wave of increasing disorganization in the universe that defines the difference between the past and the future.
So the Big Bang may have stamped the arrow of time on our universe, and everything that's happened since may simply be the drive toward ever greater disorder that began with that event 13.7 billion years ago. But if time had a beginning and disorder is always increasing, does that mean that time will have an end? What will the universe be like in the far, far future?
That for you to watch. Find a YouTube link for it. I think there's one in the previous lesson. The part about that my brain still has trouble with, other than all of it, is the idea of the pages of the book. Like, sure, there's a chance they could land in a nice orderly stacked pile in order. Like, that's one out of a bazillion chance of them ways to land. But they still wouldn't be bound together as a book. They'd just be a stack of pages. And the glass, like, sure, you could reverse all of the directions and put them all back together, like, so that they're in that shape, but they wouldn't be attached anymore. So that's the part that I just don't quite follow in the idea of it. But yeah, we've seen this example before here about the evidence of this, the life of a muon thing. So I just left it in as a reminder. But the life time slows down to the point where it has time to get there, and then the idea, also the idea of the length changing from their point of view, we'll see soon as well. I don't even have a link for that one, so I'm not sure how you'd see it. But anyways, skipping that one. The other thing I want to show you is really cool here, the other justification for time dilation itself. So let me get that queued up.
What Einstein figured out is that there's a profound link between motion through space and the passage of time. Roughly speaking, the more you have of one, the less you have of the other. To see how this works, let's take a little ride. Right now I'm heading due north, 50 miles an hour. And that means all my motion is in the northward direction. But let's now turn onto a different road and head northwest. I'm still going 60 miles an hour, but I'm not making as much progress toward the north as I was a minute ago. And that's because some of my northward motion has been diverted or shared with my westward motion. Einstein realized that time and space are linked in much the same way that north and west are. And with this surprising insight, Einstein would overthrow the common sense idea that time ticks the same for everyone. Here's what I mean. That guy over there would say that I'm not moving at all. But I am. I may not be moving through space, but I am moving through time. I mean, after all, my watch just keeps on ticking and ticking. And as long as I'm standing still, that is, not moving through space, Einstein said that all of my motion is through time. But look what happens if I walk toward that guy. We've exaggerated it, but because I'm now in motion, he'll perceive my watch ticking slower. That's because, from his perspective, some of my previous motion through time is being diverted into my motion through space. And it's not just my watch. If we really exaggerate the effect, he'd perceive all my movement, my voice, everything about me slowing down. And now that I've stopped moving, the passage of time on our watches once again agrees. This was Einstein's key insight, that motion through space affects the passage of time.
It's mind-blowing that you and I will not agree.
So, summary of that stuff there. We remember from previous sections of physics courses, this one in grade 11, that we have componentizing of velocities and so on, right? So a three-dimensional velocity, is shared between the x, y, and z dimensions, and which we calculated as components, right? So Einstein suggested that speed or velocity is shared through time also. Think of what he coined the idea of the term and thought of the idea of space-time as being the fabric of the universe, right? So yeah, Einstein proposed that a combination of an object's speed through x, y, z, and time always adds up to the speed of light. So for ordinary objects, slow speeds in x, y, z, of course, right, the majority of their speed is through time. So the idea is that we can link this to the ultimate speed limit and other things to do with time dilation itself, right? So an object's speed through space-time is always the speed of light. Stationary objects move through time at the speed of light. This is just regular passage of time that we're used to. And then the speed, right, this speed of light through time can be diverted to be speeds through space, right? And so the maximum speed possible through any space dimension is the speed of light, because that's all that there is to be able to divert, right? So, and also, of course, speed through time slows. In other words, time dilation happens as the speed is diverted. Okay, so that's a very different way of explaining the why of time dilation rather than just the what, the calculation of the equations and so on, right? And also note, of course, here that something interesting, light travels at light speed, of course, through space, right? X, Y, and Z. And so light speeds through time must be 0. In other words, light doesn't age. And so, think of that could explain how light can travel for millions of years from stars way, way away and not age. Doesn't die, doesn't dim, it just travels, right? So if anybody ever sort of asked about that or thought of that, that's a justification of it, right? So the rest of the pages here you can read through if you want, but it's just a text version of what we saw in the video. The idea of the diversion of speed through dimensions and time. All right, so that is the last bit about time dilation. There's some questions there for practice about it. And yeah, thanks for watching.